So last class we gave the four Maxwell's equations in point form. And also in the integral form. Hmm. So this much we had done in the last class. Is it okay? So from this point we will start today. Before we start the main proceedings, let us revise something which we had done in the first year. That is called phasor notation. We had already done this in first year. So just to revise, we had seen that the voltage waveform Vt will look like something like this, cos omega t. Okay. For a propagating wave, the electric and magnetic field, it usually looks something like this. These are the typical forms of E and H, which we will, of course, there will be Z, function of both Z and T. So this is the typical forms of E and H, which we will see in this class throughout this subject. Okay. Now, using a very famous law of complex algebra, we can write that e to the power of j theta, that is equal to cos theta plus j sin theta. This is the De Moivre's theorem, right? So cos theta is simply the real part of e to the power of j theta. Is it okay? So clearly, if my waveform is like this, Et, that is E0 of cos omega t, we can simply also write it as real part of E0 to the power of j omega t. Can we write it in this way, in phasor form? Note that, and this thing, this e to the power of j omega t, it is often given as et. This bar is phasor. Okay, some books they give in italics, right? Is this okay? So et is the real part of the phasor et. Is this clear? Is this okay? This we had seen in the first year. Can't hear you. Can you hear me properly? Can you hear me properly? Can you hear me properly? Yes, okay. So is this okay? Is this concept okay? This we had already discussed in first year. It's nothing new. Okay, Rakesh, I told you. You have told me about this. Others, I will upload this in YouTube so you can watch it later. Okay, don't worry about that. Other, anything? Is it okay? Or do you want me to repeat this?
Okay, sir.
Okay. Now, what will happen to the waveforms which we will see in this course? Like E, this is a T, that is E naught cos of omega t minus beta z. Say after that it is x or I or I. So what happens to that? This can be written as the real part of E0 e to the power of j omega t minus beta z. Okay. This can be written as e to the power of j omega t E0 to the power of minus j beta z. Is it fine? Can we write it in this way? Can we write it in this way? Can we write it in this way? That is the real part of. Note that this E and this E are not same. This is always real. This is always real. And this is usually complex. Is this difference okay? This is always real. And this is usually complex because it has quantity like e to the power j omega t and e to the power of minus j beta. So it is usually complex. So a real number and a complex number cannot be equal. So this EZT, this arrow, this vector and this phasor, please don't get confused between the two. Okay, they are not the same. Right? So what is the advantage of using this phasor? See that often we have things like this. Curl of H equal to J plus del D del T. Is it okay? If we use phasors instead of vectors, then we have a unique advantage, unique convenience. That is, we can write this. We can write this and see the unique advantage we are having is EZT, that is equal to e to the power of j omega t Ez, and del t of e to the power of j omega t is j omega e to the power of j omega t. Is it okay? So this differential operator can be simply replaced as j plus j omega epsilon e. Can we write this if we take phasors? If we take phasors, can we write this? See, if I had taken this cos form, then time derivative would be sine. Then we cannot have written like this. But If we take in this form, we get this very unique advantage that the time derivative can be simply replaced by j omega. Is this okay? Or I will do I want me to repeat once more? Is this okay, or do you want me to repeat once more?
Sir, can you repeat
Yes, I can repeat. I can repeat. In phasor terms, what we were writing, E z t, that was E naught e to the power of j omega t e to the power of minus j beta z. That's what we were writing in phasor terms. Okay. And the vectors, how to get back? Very simply, that is the real part of this complex number. Okay. If we take the real part, we get back to this complex number. The advantage of that is often in Maxwell's equation we encounter time things like del E del T and del H del T. Now, if this is my E, and if we take the time derivative, what we will get? Del T of E phasor of E z t, that will be j omega E naught j omega t. This we can write. If we take the time derivative del t of this, if we take a time derivative del t of this, we come to this. Is it okay or not? And see, this part is simply E z t. So del t of del t of E z t, that is simply j omega E z t. Can you say this relation? Can you see this relation? Is it okay?
Yes, sir.
Right? But if we had taken the cost form, we couldn't have written this way. The cost derivative, time derivative of cost will become sine. And cos and sine, we cannot say that cos theta is equal to sine theta for all values of theta. So if we take this, then we get this very unique advantage that the time derivative is simply replaced by j omega. Is this okay? Is this clear? Others? Any questions? Then why we are writing this? Is this okay?
Yes, sir.
Okay. So if we have, and this we can do only if we have sinusoidal variations of time variations of sinusoidal variations of E and H. So in phasor notations, curl of E, that is minus j omega b, curl of H, j plus j omega, sorry, can we write this? Can we write this? Is it okay? Is this okay? Is this equation okay? Is it fine? Okay. Now we come to the important topic of the plane waves. Okay, electromagnetic waves. That is the main, one of the very important parts of our course. The electromagnetic wave equations and solutions. Okay. We assume one vacuum. Okay. First we will solve for vacuum, then we will solve for perfect dielectrics, then we will solve for non-perfect dielectrics, and finally we will solve for good conductors. Okay. So in vacuum, what are the immediate results? A. What is vacuum? That there is nothing. In the medium, there is nothing. Okay. If there is nothing, there cannot be any electrical conductivity. Can vacuum propagate electricity? So sigma is 0. A. B. There are no charges, so rho is 0. So how does the Maxwell's equation change if sigma and rho are 0? Curl of E, that is minus mu del H del T. Curl of H, that is, and C. Obviously, epsilon r is 1. That implies epsilon equal to epsilon naught. D. Mu r is 1. That implies mu equal to mu naught. Obviously, for vacuum, epsilon r is 1 and mu r is also 1. Why there is no J? There is no J because sigma is 0 and J is equal to sigma E. That is sigma E, and this sigma is 0. So this becomes as 1. See, divergence of E is 0 as rho is 0, and divergence of H is always 0. So no problem. Is it okay for vacuum? Is it okay? Are the 4 equations okay? Yes or no? Is it okay or not? Okay, great. So let us give the names. This is my number 1. This is my number 2. This is my number 3. This is number 4. Number 4 will be complete. So what happens? Taking curl of number 1. What do we get? Curl of E, that is minus mu naught del del T, curl of H. Can we write this from this one? If we take curl of both sides, can we write this equation? Is it okay? Curl of E was minus mu naught del del H del D of H. So if we take curl of both sides, we get curl of E, that is minus mu naught del del D of curl of H. Right? Can we write that? Is this okay? Right. But curl of H from equation number 2, we had seen curl of H equal to epsilon naught del E del T. So we can replace curl of H here. So curl of E, that is equal to minus mu naught epsilon naught Can we write this? Can we write this? Is it okay? Now, what is curl of E? That is, can we, this we had already seen on the first class, right? And what is this? What is this? 0. And gradient of 0 is also 0. So in our case, curl of E, that is equal to minus of Laplacian of E. Is it okay? So what the equation we have? So comparing this and this, we can write that any doubts so far? Any doubts so far? So far, anything in doubt?
No.
Okay. Let us consider the most general case, that E equal to E x x y z d I plus E y x y z g plus E z x y z d. And note that this Laplacian, it operates on a vector, not on a scalar. So how does a Laplacian, if operate on a vector, how will it look? If this operates on A, okay, so this will be same as I del simply the scalar Laplacian operated on all the components of the vector. Okay. So our equation now, it becomes comparing the we can write this comparing the I, j and k terms. Can we write this? Is it okay? Is it okay? Oh, sorry, negative will not be there. Sorry, right. A negative will not be there. Thank you. Anything else? There will be no negative because here there was no negative. Okay? The negative sign will not be there. It's coming straight from this. Okay. Is it okay now? Sorry about this. Is it okay now? Now you see that this becomes a very formidable equation with very lot of terms and lot of differentials. So let us take some simplifying facts. First, we assume that we are considering an uniform plane wave propagating in plus x direction. What is an uniform plane wave? An uniform plane wave is a wave where all the points which are in the same phase or all the points on the given plane perpendicular to the direction of the propagation, they lie on the same phase. Which means that suppose the uniform plane wave we are considering, it is coming out of our screens. Okay, then all the points on the screen, they will be on the same phase. There will be no variation on any direction that is perpendicular to the direction of the propagation. Did you understand? Is it okay? Suppose that my wave is coming out or going in, doesn't matter. You are the screen. Then all the points on the plane, any plane that is parallel to your screen, there will be no variation. The magnitude would be the same everywhere. That means if my wave is propagating in plus x direction or in that matter minus x direction as well, there will be no y and z variation. Is this okay? If the wave uniform plane wave is propagating in the x direction, be it plus x or minus x, it doesn't matter. There will be no variation in y and z. If it is propagating in plus y or minus y, doesn't matter. There will be no propagation in x and z. If it is propagating in plus z or minus z, then there will be no variation in x and y. Right? So with that assumption, these terms vanish. If we take this assumption, then these terms vanish. The del y and del z, and consequently del 2 del y square and del 2 del z square, they vanish. Is it okay? Is it okay? Is it clear why these terms will vanish? Because since it is propagating in the plus x direction and there is no and it is a uniform plane wave, then there will be no variation possible in the y and z direction. So all the del y's and del z will be 0. So our equation is now greatly simplified. It becomes del 2 ex by del x square, that is mu naught epsilon naught del 2 ex by del t square, del 2 ey by del x square, that is mu naught epsilon naught del 2 ey by del t square, and del 2 ez by del x square, that is mu naught epsilon naught del ez by del t square. Can we write this? So the equations can be reduced to this form. Is it okay?
Yes.
Now, can there be any further simplification that is possible? Let us see. We also have this from Maxwell's equation. We can write this. Okay. Let us expand this. What we get? We can write by expanding the gradient. Okay. But from the plane wave assumption that del y and del z must be 0. So the second and the third terms, they are vanishing. Is it fine? Is it okay? Can we write this? Can we write this?
Yes, sir.
Okay. So we come at this point that del ex by del x, that is 0. Okay. Now, if this is 0, then of course this will be 0. If this is 0, then clearly this will be 0. There is no other possibility. This is first point. Is this clear? Okay. Now, let us see the fun. Correct? Right? Agreed with this? We can put a 0 here. We can put a 0 here. Okay. Now, this is clearly not equal to 0. This is a constant value. Cannot be 0. Similarly, this cannot be 0 either. Neither mu naught can be 0 nor epsilon naught can be 0. They are constant things. So if this has to be 0, then this must be 0. Agreed? Okay. Now let us look closely that when this can be 0. Can anyone tell me when this can be 0?
Sir, when the X is independent of T.
I do not catch that. Sorry. One second. Let me increase the volume. Already. One more time.
Sir, when Ex is independent of T.
When Ex is independent of T. Excellent. When Ex is independent of T. Or can Ex del to Ex del T be del T square be 0 in this case? This point is very taken. Can this be 0 here? That when Ex is equal to K times T, K is the constant. Can it be 0?
Yes, sir.
Yes, this can also be 0. Okay. Now think carefully. We are discussing about wave. What is wave? What is a wave? If we have something, some phenomenon at a particular point, at a particular instant of time, suppose we have some, there is some disturbance here. Okay, this point is x naught and this time is t1. Then we expect the same disturbance, exactly same thing, at some x1 at time t2 such that x1 minus x0 that is equal to v t2 minus t1. Is it okay? If this is a wave, we can say this. Can we say this? Where v is the, of course, the velocity of the wave. Is it okay to say this? Can we say this? That if there is some disturbance, something at one point of time, at one position, at one point of time, then the same disturbance will repeat itself in other positions, in other points of time, such that this equation is satisfied. Can we say this? This I am showing it in one dimension, can be in two dimension, three dimension. Is it okay? Is it okay? Is it fine?
Yes.
Okay. Now, can these things be part of a wave? 1 and 2. Can these be waves? What do you think? If we discuss waves, can these be any type of wave? This simply means Ex is independent of T, means this is like this. This is my Ex, this is my T. And the other possibility Ex equal to KT, that means like this. Do you think this could be waves? Here, if I see this here, we will not see the same value anywhere for any other T. And here there is same thing everybody will also call these. Okay. So can we say that these are waves here? So neither of them can be part of any wave motion. Do you agree with this or not? Neither possibility 1 nor possibility 2 can be a wave as such. Do you agree with this or not?
Yes.
Okay. So what is the only possibility we have? What is the only possible thing we have? How to make this a wave? Only possible, what can we do? Any idea? What is the only possibility? If Ex is independent of T, cannot say that. When Ex is like increasing linearly, we cannot say that. Then what can be the only thing that is possible? Anybody? What is the only thing that is possible? Can try. Ex is 0. Then there is no problem. We do not have to bother about Ex if Ex is 0. Is it okay?
Yes, sir.
So we come to a very, very important property of an algebraic wave. That is, similarly, we can show that Hx is also 0. Similarly, we can prove. The way we had proved that, by the way, the way we had proved that this was true, you should also try to prove that this also holds. Okay, I can do the very same analysis with H also. We get the very same equation, the same wave equation. Okay, and by similar logic, we can also show that that Hx is 0. So if my uniform plane wave is propagating in the x direction, then Ex and Hx must be 0. Okay, is this clear? There cannot be any component of E or H in the direction of the propagation of wave for uniform plane waves only. For guided waves, it is possible. Okay. next 7th semester when we study microwave, we will find waveguides. Okay, there you will see that it is possible that there could be Ex or Hx in the direction of the propagation. But in case of uniform plane waves, it is not possible to have any electric or magnetic field in the direction of propagation. Is this concept okay? Is this clear? That is the reason plane waves sometimes called TEM waves. TEM full form is transverse electromagnetic. This means that in the direction of propagation of the wave, there cannot be any component of electric or magnetic field. Is this concept clear?
Yes, sir.
Yes, sir.
Okay. Any questions so far? I will continue the next session. So whatever time is there, let me take your attendance. And if you have any questions, I will write on.